Recall that del f is the partial of f with respect to xi plus the partial of f with respect to yj plus the partial of f with respect to zk for a scalar function f, and that del f is the gradient of f. Here we're going to see a different way to use the del operator. The del operator is that upside down triangle with a vector on top, so the del of del f. But here we're defining it as a vector that doesn't really mean much all by itself. The partial with respect to x, comma, the partial with respect to y, comma, the partial with respect to z. And it's actually just three partial derivatives that aren't acting on anything until you give it something to act on. And just for some context here, an operator is something that acts on functions. We've seen them before. The derivative is an operator, right? So I wrote that as a partial. The derivative with respect to x, it's an operator, and it acts on a function f of x. It doesn't have meaning until it acts on that, but it tells you what to do. Likewise, an integral is an operator. It acts on a function, say f of x, right? The integral symbol by itself doesn't have any meaning, but when you pair it with a function, then it does. The del operator is it's similar in that respect. It has meaning when it operates on a vector field f equals pi plus qj plus rk. It can act on these vector fields in two ways, and that's what this section is about. The first one is called the curl of f. It's denoted by del cross f and is equal to the determinant that has as its first row ijk. The second row are these partials, partial with respect to x, partial with respect to y, partial with respect to z operators. And then the third row is it comes from the components of f, which is p, q, and then r. We compute this the way we would compute any determinant. And so we cross out the row and column that contain I, and then what's left is a determinant that we compute, but it tells us what the partial derivative operators are acting on. And so we have the partial with respect to y is going to act on r. So that's going to be the partial of r with respect to y minus the partial of z, the partial with respect to z is going to act on q. And so we get the partial of q with respect to z, and that's going to be the I component. Usually we subtract for the j component, but this time I'm not going to do that. We're going to fix that in a different way. We're still going to cross out row and column that contain j, and then form a determinant of what's left. And we have here, it would be partial with respect to x acting on r first, but we're going to reverse that because we used a plus instead of a minus. And so we're going to say we have here the partial of p with respect to z minus the partial of r with respect to x times j. Finally, we have crossing out row and column that contain k. We're going to be left with the partial of q with respect to x minus the partial of p with respect to y, and that will give us the k component. That's referred to as the curl of f. Note that because it was a cross product, the result is a vector field. We're going to jump right into a theorem. If a scalar function f of x, y, z has continuous second-order partial derivatives, then the curl of del f is equal to the zero vector. In other words, if f is a conservative vector field, then the curl of f is equal to the zero vector. By the contrapositive, if the curl of f is not equal to the zero vector, then f is not conservative. Notice that the statement doesn't say that if the curl of f is equal to the zero vector, then f is conservative. We don't have that here. We'll come back to that idea in just a minute. First, we're going to prove the theorem. Del f, as you know, is defined to be the vector that has the components partial of f with respect to x, the partial of f with respect to y, and the partial of f with respect to z. So that means that the curl of del f is equal to, as we just saw, a determinant, the top row of which is ijk, the second row of which is the del vector, so the partial with respect to x, with respect to y, with respect to z, and then the bottom row would be del f, which is the partial of f with respect to x, and then y, and then z. By computing this cross product, we're going to find that our components, so I'm just going to set it up here, I, j, and then k. Our components here are actually going to turn out to be second mixed partial derivatives. Crossing out row and column that contain I, we have the partial with respect to y acting on the partial of f with respect to z. That gives us the second partial of f, first with respect to z, and then with respect to y. The other portion of this is the partial with respect to z acting on the partial of f with respect to y. And so we get the second partial of f, first with respect to y, then with respect to z. So here we have mixed partials involving z and y. You can confirm that the j component involves mixed partials with x and z, and the k component involves mixed partials with second mixed partials with y and x. Folks, this is going to equal 0 by Clairaut's theorem, which says that second mixed partial derivatives are equal, and so if I subtract one from another, I should get a bunch of zeros. As I said, this statement was an if-then statement, and the converse is not necessarily true. However, in certain situations it is. So we can say that if f is a vector field on all of R3, and its components are functions that have continuous partial derivatives, and if the curl of f is the zero vector, then f is a conservative vector field. The reason this isn't a strict if and only if is that here f has to be defined on all of R3.